I call it the size and scale of the universe from the top of the ladder. It's kind of a two-part thing. I'll show you why. So we can get rid of that thing at the top here. Not sure how. Yeah, anyway. All right, so the first part of this is kind of just to give an idea, and it's probably going to be very very simplistic for the audience that's here. But talking about the just the size of the universe, and there's a reason for that because it kind of leads into the second part of the presentation. So. Moving on, if you were to give your cosmic address, starting with the way we usually give addresses, street, city, state, country, moving on to hemisphere, planet, orbit, we get into star, and then whatever comes behind that, after that. If you were to go ahead and give your address, I don't know which under what circumstances you would go beyond that, but anyway, let's continue on from there. If you were to build a scale model of the universe using the Earth as a base, and going all the way up into the corner here, using the Earth as a grain of salt. This table kind of describes how large all the other components would have to be to fit into a scale model. I think we've all seen, let's say the pictures of the solar system. You've got the sun, and you've got all the planets. 8 or 9, depending on how old you are. In fact, you could never draw a picture to scale solar system, because the planets, if you were to take I don't care how big a sheet of paper to use, if you were to draw a picture to scale of the sizes of the planets, they would be they would be too small to see on a piece of paper, and the distances between them would be impossible. Astronomical. That's a good word for it. They'd be impossible to fit on a piece of paper. The sizes and the scales are just outrageously small. The next slide actually fits all these in. If you use the Earth as a scale of 1, size of 1, and this fills in all those sizes. And so if the Earth is the size of a grain of salt, and these unfortunately are millimeters and in metrics. I still have trouble sometimes wrapping my head around metric sizes. Well, if the Earth is a grain of salt, then the sun would be the size of a gumball. The solar system would fill a football stadium. The solar neighborhood, and that's kind of defined a little bit later, is the size of the moon. The whole galaxy is the size 5.4, so the width of 5.4 suns. The local group of galaxies, which I believe is everything within 40 light years of the sun, would go out to the orbit of Mars at that scale, all the way down to the universe, which goes out about 3/4 of a light year at that scale. The other columns in this are almost, the numbers are almost meaningless, but they do give a more realistic, a more real representation of the actual sizes of where things are. We're used to thinking of, the light that we see as being, the universe being 14 billion or just under 14 billion light years old. But because of expansion, the universe is actually 91 billion light years in diameter.
Because there's parts we can't see.
Well,
Because of the
because of the expansion, it's in 14 billion years, the universe has expanded 91 billion years. Right. It may actually be quite a bit bigger.
Chris, the Webb telescope took a picture of a dark spot in the sky.
Oh, yeah.
And when they processed it, there was more galaxies than stars in it.
Oh, yeah. Oh, I know. And that dark spot that it took was, I believe, about a millimeter and a half by a millimeter and a half in diameter, in diameter. And there was something like on the order of 10,000 galaxies within that one picture. Yeah. So when we talk about the, for us here, the top of it is being wiped out, but when we talk about the realms of the universe, start with the Earth, go to the solar system, basically not the scale, go to the Milky Way galaxy, then the local group, then the local super cluster, and then the universe. So, and again, some of this is very simplistic. This part of the presentation was meant for a very basic audience. Everybody, we all know all of this information about the Earth. Obviously, it's the planet where we all live. It's a rocky planet. It's not really round. It's spherical in shape because generally, even a rocky planet, if it spins, it is spherical, but it's also not perfectly spherical. Anything that spins is going to be wider at the equator than it is pole to pole.
Like an oblate spheroid.
Oblate spheroid. Thank you. I didn't know I was looking for that word, but apparently that's the word I was looking for. At the speed of light, it takes 0.13 seconds to go all the way around the Earth. That beam of light that goes around the Earth at the speed that it's traveling does experience some serious relativistic qualities. Even this has nothing to do with the presentation, but I just found out that the navigation satellites, which travel at 18,000 miles per hour, because of the relativistic speed, the relativistic effect that they undergo because of that speed. If their clocks weren't adjusted, your GPS signal would be off by 6 miles per day. That's a huge error.
Well, the satellites are geosynchronous, right? Like they stay over the same spot of the Earth as it goes around?
Well, yeah, but they still move.
Oh, they have to. Yeah.
Well, they do stay. Actually, I'm not sure if they stay over the same spot, but they do move. They do orbit at it.
Are you saying they precess?
Am I saying what?
They precess?
I don't know that, John.
I don't think they're geosynchronous.
I
remember seeing on the little machine, like
Yeah,
the old type when you had to like some of them were coming into view and some of them were going out of view. So I don't think
Yeah,
they're,
I don't think they're geosynchronous. But I was kind of amazed by the amount of error that they that they encounter because of the speed at which they travel. And a lot of that is actually due because of their altitude and how far they are away from the center of gravity. So anyway. And then then we have the sun, of course. Everybody knows this. I'm just gonna skip this part here. All right. How do I get rid of that bar? Oh, okay. All right. So if we go to the solar system now, we know that the heliosphere of the sun, that's the boundary between the solar wind and the interstellar space, is about 100 astronomical units from the sun. Pluto orbits about 40 astronomical units from the sun. The heliosphere or the solar system basically is distributed in a flat disk, unless you count the Oort cloud. That's more of a beach ball shape. And then we get into the fun stuff. That's the solar neighborhood. If we get outside the solar system, we're looking at the solar neighborhood. That's the region of the galaxy within about 20 light years of the sun. So it's an area about 40 light years in diameter from the sun.
Excuse me, Chris.
Yep.
This slide before,
Yep.
I think it's good to call out. John just sent out an email for a Voyager webinar that's going to happen on tomorrow, Thursday the 20th at 9 p.m. Eastern. And she will talk about how the sun makes waves out to interstellar space. That looks like a really interesting talk.
Yeah.
They'll discuss the plasma, magnetic field, and particle environment from the sun to the interstellar medium surveyed by Voyager 1 and 2.
Yeah. No, I'm sure it'll be interesting. The picture in the lower right, which is pretty interesting. What you're looking at there, as the sun moves, as the solar system, the entire solar system moves through the Milky Way, it does create a bow wave. It almost like a boat moving through the water. And the bow wave in front of the solar system is compressed and it stretches out behind it. So where Voyager went is leading the sun. So it went through I believe it went through the narrower part of that heliosphere into interstellar space. Well, yeah, this should be a good talk. Okay. The solar neighborhood, again, is stars that are within about 40 light years diameter, which is kind of an interesting interesting number. We've been sending radio waves out into space now for how long? Since the early 1900s. So all those stars are well within the amount of time that if there's anything out there listening, they're well within the range of time when they could have heard it and sent signals back. But
Well, how many are?
I don't know. I don't know. I mean, a lot of those stars are red dwarfs. But there's a lot of stars that are planets too, like the Gliese system is here somewhere. Oh. And then beyond that is the Milky Way galaxy. And we are here in the Orion spur of the Milky Way galaxy, about 30,000 light years from the center. And we do orbit the center of the Milky Way galaxy, about 250 million years to complete one orbit. All those stars that you saw in the previous slide orbit with us as a group. So. And then we are part of the local group of galaxies, which contains three large galaxies, contains M33, the Andromeda Galaxy and the Milky Way Galaxy, and then dozens of dwarf galaxies, which are all gravitationally bound in a space of about 6.5 million light years across. And then the local group is part of a local supercluster. And the largest part of the local supercluster is, I believe that's here, the Virgo cluster. And the clusters and the groups are all gravitationally bound together. The individual clusters are gravitationally bound together, but the members of the superclusters are not. They're actually spreading apart because of the expansion of the universe. And then beyond that, it actually is the next size level is the universe itself, or at least the observable portion.
Billion galaxies.
100 billion galaxies. And that number is probably changing all the time. So to me, this is the more interesting part of the presentation. Is how do we know these distances? You know, we've gotten pretty good at measuring all these distances in space, but how do we do that? So if you're standing in a dark cave, and you light a match, and there's a light somewhere out there in this dark cave. How do you know if the light you're looking at is somebody else holding a match? Or is it a town? Is it a large light? Without some perspective to match it against, a light is just a light. You don't know if you're looking at a small light close by or a very large light far away. So how do we measure distances and how do we measure the distance to lights in space?
Standard candles.
Well, that's only one way. Yeah, standard candles. We use what's called the distance ladder. The standard candles are only one part of the ladder. So there's basically two basic methods. But again, those are only two basic methods, along with some others, standard rulers and standard candles. We start with standard rulers, which are used to measure shorter distances. Parallax, moving clusters, time delays, and water masers. So parallax, a lot of people are probably familiar with parallax.
That's right.
You know, the parents shift in
Months
position.
apart.
Yeah. Well, yeah, 6 months apart. Parallax, the parents shift in position against background stars as the Earth moves in its orbit. You know, it's if you ever took geometry in middle school or grammar school or whatever, if you have a triangle has 6 components, it has 3 sides and 3 angles. As long as you know any 3 of those components, you can calculate the other 3 parts of that triangle. By doing a parallax measurement, you can figure out 1 side or 2 angles. And what that will give you is it'll give you the distance to the object that you're measuring. Moving clusters, see, these are things I never knew. Moving clusters are a specialized measure used to measure the distance to star clusters by using their proper motions and Doppler shifts. And it was actually used historically to determine distances to clusters like the Hyades and the Pleiades. I don't think it's used for much anymore nowadays. But these are not standard candle measurements. These are more direct measurements. And then time delays. By observing the light from distant objects that's bent around massive galaxies. And figuring out the difference in the arrival time of the images. I'm not really sure how this works. Apparently it does.
Light bending around massive galaxies.
Yeah.
Well,
Yeah, well, it would be, gravitational lensing. I don't know how that's used to determine distances, but then water masers are kind of fascinating. Water maser is a type of element that gets created and excited around stars too, but for these purposes, it's created around supermassive black holes, and it's always created at a particular distance away from the supermassive black holes. So if you're looking at a galaxy, you can determine how far away that galaxy is by measuring the intensity of the mega maser that's created within that galaxy.
stimulated mission.
It actually is molecules of water.
Yeah.
And it's used to measure distances to galaxies as far away as 50 to 200 million parsecs.
Molecular and
So again, this is, parallax. And it's limited to relatively close objects. We do have a limiting baseline for direct measurements, for direct viewing for terrestrial telescopes of 186 million miles. Because we take a measurement in the spring or the summer and then take another measurement in the winter when we're on the opposite side of the sun. But the longest baseline we can get by doing that is 186 million miles. And the Hipparcos satellite is a very useful tool for doing that. But again, that's still just orbiting the Earth. So the baseline isn't any longer. And the Hipparcos satellite has been very good at doing that. It eliminates any interference from the atmosphere, and it's done accurate measurements for stars within 1,500 light years of the sun.
So that measurement really is dependent on the accurate measurement of an astronomical unit, which was an extraordinarily difficult measurement to make in the early 20th century.
Yeah, and I've got a few slides following on that actually, which was kind of a fascinating thing to come up with. Thank you, stranger who I don't know, for your segue. Yeah, the astronomical unit was a combination of measurement methods were used to come up with the astronomical unit, which was really fascinating the way this worked out. So it started with Kepler's third law of motion, which basically says that he figured out that there's a relationship between the period that a planet takes to come to the period of rotation, the period that a planet takes to go around the sun, and its semi-major axis. Basically it's the radius. The longest axis of its orbit. There's a direct relationship between those two components of its of the planet's travel around the sun. So once you knew how long a planet took to orbit the sun, you could figure out how far, well, you could come up with the ratio of how far away from the sun it is. Not necessarily the distance, though. Yeah. So using Kepler's third law, he devised this table. Actually, devised this table up to Saturn because at the time of Kepler, Saturn was the end of the known solar system. So what he knew, what astronomers knew at the time was that the Earth was one astronomical unit away from the sun. But we didn't know what an astronomical unit was. We didn't know how far it was. We just knew that it was one. And we knew that Venus was 0.72 of that. We knew that Mercury was 0.39. We knew that Mars was 1.52, Jupiter, Saturn, and so on. Again, Uranus and Neptune were not known at the time. We knew the ratio of their distances from the sun. We didn't know the values. It was up to somebody else to discover the values. This is just, how triangulation works. So what happened was in 1672, there was an opposition of Mars, where Mars was directly opposite the Earth and the Sun, which basically means that it was at its closest approach to the Earth, which allowed Cassini and his assistant to measure the parallax of Mars from two different locations, Paris and French Guiana. I don't know what the distance is, but that allowed them to measure pretty accurately using the parallax method the distance to Mars, from the Earth to Mars. They got a distance of Mars to 34 million miles, its closest approach. So now they had a number to plug in here. Right, so they have a number to help plug in a number here. The distance from the Earth to, if they knew the distance from Earth to Mars, then by playing around with the numbers, they could figure out the other distances, what the distances between the planets had to be. And I'm not going to try to do the math right now. So anyway, the parallax method was used to calculate the distance from to the sun. What he came up with for a distance of the value for the astronomical unit was about 87 million miles, which is close. It's about 7% off of the actual figure of 93 million miles. So
It's 93 million.
Yeah.
It's pretty good.
Yeah, it's pretty good. Pretty close. So anyway, those were the methods for the standard rulers. Objects that are further away are measured using standard candles. The standard candles example are Cepheid variables, type 1A supernovas, TRGB, and Tully-Fisher. All right, Cepheid variables, again, are stars that pulsate with brightness in a stable period. And they have an intrinsic brightness that's directly related to the pulsation period. If we can measure their pulsation period, it's very short. And if we know their pulsation period, then we know that how bright they're going to be at their peak pulsation. And if we know their peak pulsation, then we can, if we know their peak luminosity, then we can determine how far away they are. So that thereby they become a standard candle. Type 1A supernova are white dwarfs in a binary system that pull material from the companion star. And they pull enough material where the white dwarf then accretes enough material to go supernova. And they do it with a consistent because white dwarfs are always the same size. They always pull the same amount of material from the supernova at a consistent luminosity. So when we find a type 1a supernova, we can tell how far away it is by how bright it appears to us.
So prior to a star going into the supernova phase, do we know where that star is, or do we have to wait till there's a bright flash and then work backwards from that?
I'm not sure how it works with a type 1a. With a type 2, a type 2 supernova, we have sometimes a few seconds, sometimes a few minutes warning. Because they release a flood of neutrinos. I'm not sure if a type 1a supernova does the same thing.
Neutrinos.
Yeah.
Okay, yeah,
Yeah,
they release them.
yeah.
I think it's less to do with the star before the supernova, and more to do with the apparent luminosity of the supernova. The idea being is that type 1As have a peak brightness that is consistent. And so if
Right.
you know what that brightness is and compare it to the apparent luminosity, you can find the delta.
Yep.
That assumes that the luminosity is correct, and there's been recent papers that have been delivered that actually call that assumption into question.
Really? Okay.
There are some supernovae, type 1 supernovae that shine brighter than the standard range and fade faster. The term that is something like a super Chandrasekhar star. Um, So I don't know. Some of that's beyond my understanding, but that the follow on to that, the headline that caught my eye was that this may be one reason why we have some discrepancy in the Hubble constant.
Oh, okay. All right. So the TRGB is a tip of the red giant branch. What when uh, a regular size star, not a giant star, but a regular size star like our sun, or typical size star like our sun, goes into its red giant phase. There's a point it reaches where it levels out in luminosity, and all stars that are a normal non-giant size will reach that phase at some point near the end of their red giant phase, and they will level out, and their luminosity they will get to that standard luminosity phase. And at that point, they become a standard candle. It's called the tip of the red giant branch. And then the last one is the Tully-Fisher relation. And this deals with entire galaxies. It's a the luminosity of galaxies is related to their rotational velocity. So it's a method used to determine the distance to an entire galaxy, depending on its rotation speed. I won't even pretend to know anything about this one. And there's just some detail about Cepheid variables. I guess the Large Magellanic Cloud contains hundreds of them, all at the same distance. And that was used to really work out the relationships, the details and how to work with them.
So it was that relationship that Hubble's female computers, the woman that was leading the computers, identified that to him as being that chart on the left, the lower left, showing that the distance is correlates with the periodicity of the variable. So that demonstrated that Andromeda was in fact an island galaxy in its own right, away a significant distance away from our galaxy. Beforehand, they thought that Andromeda could be something like a globular or a specialized cluster that was a long way away in our galaxy. But then Hubble used, and Hubble's team used this in order to define the fact that all of those other galactic nebulae were in fact a great distance away.
No. Okay. Thank you, Bill. And again, just some more detail about the type 1A supernovae. And this is just a diagram of showing the tip of the red giant branch. Shows the star coming off the main sequence, growing as a red giant, and then it reaches a point here, where it comes off the asymptotic red giant branch and gets to this stable point, where it continues. Oops. Yeah, where it stays stable for continues cooling to the point where it becomes a planetary nebula on a white dwarf. And for a very long time, it stays stable at a particular luminosity point. So this is the it doesn't look like a ladder, but this is really the cosmic ladder. But there's a couple of points where it's bracketed by two methods that we really haven't talked about, and that's radar ranging and Hubble's law at both ends. A radar ranging, pretty self-explanatory, where radar or radio waves or radar or some kind of transmission is used to directly bounce off an object. It's really limited. No, it's a relatively new process limited to nearby planets and asteroids. And Hubble's law is the redshift, the measurement of a celestial object's redshift. And it's a measurement of how quickly an object is receding away from us to estimate its distance. So those are the closest rungs and the furthest rungs, and that's it. Now, all of these techniques do kind of build on each other. And there are others in here that are either specialized to particular celestial objects, or that I haven't talked about. Like, I'm not sure what GCLF is, and anyway, there's more that fits somehow into the distance ladder that I haven't really talked about. But there's quite a few methods that we can use, from objects that are very close by to the earliest objects in the universe, and get a relatively accurate reading, or at least we think it's a relatively accurate reading of the distances. So anyway, so if you're in the dark cave and you got a match lit and you see the light in the distance, sometimes you may not want to know what those lights are.